Okay, guys, I'm not even sure if this is recording. Let me check. It is. Okay. So this is, I just cut and pasted the data table. You guys should have it in front of you. If you don't have the free response question in front of you, it's in the folder. It's 2013. So this was the last test that my students took because you guys didn't take it last year. A student was assigned the task of determining the enthalpy change for a reaction between solid MgO and aqueous HCl as represented by the net ionic equation below, period. The student uses a polystyrene cup, calorimeter, and performs 4 trials. Data for each trial are shown below. First question, which is the limiting reactant in all 4 trials, HCl or MgO? Justify your answer. Now, I think the way it's worded with which is the limiting reactant in all 4 trials, they're telling you it doesn't matter what trial you pick. In all 4 trials, they set it up so that the limiting reactant was either HCl or MgO. So a little bit talking about, totally lost my train of thought. So let's just pick a trial. Oh, I know what I was going to say. You got MgO, which reacts with HCl, and it actually makes MgCl2 plus, I think H2O. Don't go there. But anyways, who cares? They want the net ionic. MgO is a solid, and then HCl is a strong acid. Just here's the net ionic equation. And then, oops, maybe I did that wrong. What's the other thing? Oh, yeah, H2O. Remember, pure liquids and pure solids get left alone. And then strong acids, blah, blah, blah. That's neither here nor there. You don't have to know this. Guys, limiting reactant problems. What we're going to do is we are going to do 2 stoich problems. I'm going to use trial 1. So in trial 1, if you look at your sheet, in trial 1, you have 0.25 grams of MgO, and you have 100 milliliters, 100.0 milliliters of this. And the question is, and pick a reactant, only reactant, it doesn't matter which one. I'm going to pick this one. I'm going to stop at moles. The reason I'm going to stop at moles is they just want to know the limiting reactant. They don't want to know how much Mg+2 you make. They don't want to know how much, oh, sorry, I dropped something here because there's a 2 here and a 2 here. They don't want to know how much Mg+2 you make. They don't want to know how much water. They just want to know which one runs out first. Now, the cool part is that just stop at moles, because you're going to work this problem twice. And remember, on limiting reactants, the smaller one is the right answer, because when one of the reactants runs out, the reaction stops. So what we're going to do is, I'm going to switch colors. The most important concept in all of chemistry is the mole, because that's a mass. I have to calculate the molar mass of MgO, which is 24.30, 16.00. I get 0.3. This is 40.30 grams per mole. Now this is interesting. This is milliliters. It's not going to get me, molar mass doesn't cancel with liters. I need the molarity. And if you look at the table, they told you it was 1 molar, which means moles per liter. If you remember way back, this was a first trimester of your junior year. The most important concept of all of chemistry is the mole. If the given or the unknown is in moles, you don't need a conversion factor. Okay, so I'm going to do this problem first. I'm going to do this problem second, and then I'm going to compare the answers, and I'm going to go down here a little bit and extend the page, switch color. So here's what I do. First one, 0.25 grams of MgO. Most important concept in all of chemistry is the mole. There's 40.30 grams of MgO in 1 mole of MgO. For every 1 mole of MgO, you will get 1 mole of Mg+2, because you always go to a product. I just picked the first product, cancel this, 0.25 times 1 divided by 40.3 times 1. My calculator, when I practiced this at home, said 0.00620 moles of Mg plus 2. Now I do the second problem, but because molarity is moles per liter, I'm going to convert milliliters to liters by sliding the decimal point over 3 places. You have 0.1000 liters of H plus. Liters is on the top, so you have this solution is made so that there's 1 mole of H plus per liter of solution. And then this is the crazy part. If you look at the balanced equation, you need 2 moles of H plus to make 1 mole of Mg plus 2. And so this cancels with this, and if I do this problem, I get 0.0500 moles of Mg plus 2. And if you notice, 0.006 is a smaller number than 0.05, and all they asked for the limiting reactant. Well, if this is the smaller answer, then this is the limiting reactant, and so the answer is MgO is the limiting reactant. Now, if you look at the scoring guidelines like I did, because after I work a problem, I always look to see if I did it right. It says you get 1 point for the limiting reactant, and you have to have calculations to justify why you picked your reactant. And so I think that would do it. All right, now the question 2 is interesting. I wish I had the chart, but here's the thing. One of these trials does not belong. And I think if you take the time to do this, and I remember when I worked this problem 2 years ago, after I explained it, the kids thought, oh my gosh, I'm an idiot. So what happens is when I'm going to calculate delta T first, because, by the way, MgO is a base, HCl is an acid, acid-base reactions generate heat, and so in trial 1, the temperature went from 25.5 to 26.5, so trial 1, delta T is 1 degree Celsius. Trial 2, the temperature went from 25 to 29.1. This delta T is 4.1 degrees Celsius. Trial 3, the temperature went from 26 to 28.1. So this delta T is 2.1 degrees Celsius. And then this delta T, trial 4, it went from 24.1 to 28.1. So this is 4.0 degrees Celsius. The other thing I want to show you, I'm going to switch colors, but in this one, we used 0.25 grams of MgO. On this one, 0.5 grams of MgO. This is 0.25 grams of MgO. And this is 0.50 grams of MgO. So some things I want you to see is these masses are the same, and these temperatures are very close. These masses are the same, and these temperatures are a degree apart, not a tenth of a degree apart. Now here's the other part you have to realize. 0.5 goes up 4 degrees. You would expect 0.25 when you have half as much of this and it's the limiting reactant and everything else is the same. You would expect this temperature to be half of 4, which is 2. So explaining all that, the trial that doesn't make sense is trial 1, and they want you to go back to that original table and draw a line through trial 1. And here's why. According to this, if you put in half a gram of MgO, it goes up pretty close to 4 degrees. See how those match? Because these match, if you use half as much of this, you should have a temperature change that's half as much. So this makes sense. This trial 1 is the trial that doesn't make sense. Okay, C is why I picked this problem. C says, Calculate the magnitude of Q, the thermal energy change when MgO it was added to 1 molar HCl. Include units with your answers. And then it says, don't use the data from the trial you just crossed off. So we cannot use trial 1 data. So here's the deal. Q equals MC delta T. I just, so they want Q. The hard part is mass. I'm going to come back to that. They gave you the heat capacity. They gave it to you as 4.81 joules per gram degree C in the writing. And I'm going to use trial 2 because I'm just anal and I do them in order. Trial 2. In trial 2, the delta T was 4.1 degrees Celsius. And it is positive. And that comes from T final, which was in trial 2, 29.1. And then T initial was 25.0. And that's delta T is 4.1. Now, the math is crazy, but it's not that bad. So here's the deal. Here's how you get the mass. I'm going to put it over here. The mass of the MgO in trial 2 is 0.50 grams. Okay? Now, here's the crazy part. You put in 100 milliliters of HCl. That's not a mass, but they told you that the density of HCl is 1 gram per milliliter. So if you have 100 milliliters of HCl and the density is 1 gram per milliliter, milliliters cancels with milliliters, and you have 100 grams of HCl and conservation of mass. If you have 100 grams of HCl and 0.5 grams of MgO, what's the total mass in the styrofoam cup? It's 100.5 grams. I hope that makes sense. This is 100.5 grams. Now, if you look in the scoring guidelines, and you should, they actually have 3 different answers, because if you use trial 1, you get a different answer than if you use trial 2, you get a different answer as if you use trial 3. So now, sliding down here and extending the page, Q is going to be 100.5 grams times 4.184 joules per gram degree C times 4.1 degree C cancels with degree C, grams cancels with grams. I did this on my calculator when I was practicing, and I got 1,700 joules. Or you could also do 1.7 kilojoules. Either one of those is the answer for C. I hope that makes sense. It's not that bad. All right, D. You're going to feel D is pretty easy, but my kids 2 years ago felt really stupid because determine the student's delta H for the reaction. So basically, this is what you got to know. Delta H units, delta H, okay, I just need to write this a different way. Delta H units are kilojoules per mole. Okay, now we know kilojoules. In trial 2, we just figured out that so to get delta H, we take 1.7 kilojoules. That's the answer for C. And then we have to figure out how many moles of the MgO, because that's the limiting reactant, you used to get that 1.7. And so what you do is you take the trial 2, you have half a gram. Well, we know that there's 40.30 grams in a mole of MgO. And so I do this on my calculator, and I get 0.0, okay, I'll just do it. I'm going to go one place bigger. So 0.5 divided by 24.30. And when I do this, I'm going to go 0.0, and I'm going to tell you why I'm stopping here. 0.02141, 0.01241 moles. This has 4 sig figs. This has 2. On your intermediates, keep 2 more than you can keep in your final answer, because then you won't have rounding error. And now we're almost done. We're going to take 1.7 kilojoules, which is the heat for 0.01241 moles, and we're going to convert that over to what it would be in kilojoules per mole. So I do 1.7 divided by 0.01241, and I get 137 kilojoules per mole, but I need to make it negative. I might now need to go back and fix. So this is crazy. Where did the negative come from? Well, the heat is leaving the chemical reaction and going into the water. And because the temperature went up, it's exothermic. So right here, a delta H needs to be negative. You have to tell people it's an exothermic reaction. Now, going back a slide, this is interesting in that in B, it's specifically worded, C. Calculate the magnitude. The magnitude means absolute value. Calculate the magnitude of the thermal energy change. So what they're telling you in part C is, I just want to know the number. I don't care if it's exothermic or endothermic. Just tell me the magnitude of Q. Because the crazy part about heat problems, and I know it was a long time ago at the lab, but these, when you put MgO and HCl together, this is an acid base, and this is an exothermic reaction. And the water is the surroundings. The MgO and HCl is a system. The water is the surroundings, and so the water temperature goes up, and that's what you measure. But that's going up because the heat is exiting from the chemical reaction and going into the water, and that's why you just have to put the negative sign on the end because the temperature went up. All right, and so now then this E is pretty easy, enthalpies of formation, so they gave them all to you, and you don't have to look them up in the back of the book. And the question is, using the heats of formation, not the bond energies, delta H is the sum of the heats of formations of the products minus the sums of the heats of formation of the reactants. And so what we're going to do is just take them off the table. So delta H, the first product is Mg plus 2, and it looks to me like that is negative 467 kilojoules per mole. And then we are going to subtract off, and then the other product is water, H2O liquid, so we're going to add negative 286 kilojoules per mole. Okay, so this is Mg plus 2, this is H2O. They both have ones in front of them if you go back to the balanced equation. And then we're going to subtract, and then the MgO has a 1 in front of it, so I don't have to multiply. So we're going to subtract because it's minus reactant, so subtracting a negative is going to be a positive. And then we're going to subtract 2 times H plus, but H plus is the most stable state, and so if you look at the table, that's 0. And so when you do negative 467 plus negative 286, minus a minus is a plus, plus 602, you get that delta H is negative 151 kilojoules per mole. That's actually a pretty easy problem. And then the very last problem is the accepted value and the experimental value do not agree. If the calorimeter leaked energy to the environment, would it help account for the discrepancies in the value? Explain. All right, in other words, our experimental value was negative 131 kilojoules per mole. The theoretical value The one that you get from the tables is negative 151 kilojoules per mole. I lied. This is 137. Okay, in other words, this is our answer for E, and this is our answer for D. And the question is, now when you're doing this, this is what I tell the kids to do on heat problems on AP. Just ignore the sign. Look at the magnitude of the number, okay? And then it works the same. Just look at the number, ignore the sign. If it's exothermic at the very end, we slap negatives on them. If it's endothermic at the very end, we slap positives on them or leave them. Okay, so here's the deal. Not because any heat lost by the chemical reaction is gained by the water, and so the numbers are the same. They're the same. The only thing that's different is you have to reason out the sign. Just go with this. On part F, the first question is yes. Yes. Because 151, I'm just looking at the absolute value, we're just looking at the magnitude. 151, the absolute value of negative 151 is bigger than the absolute value of 137. In other words, our experimental value is too low. When would it be too low? Is if you lost some heat. Okay, you lost some heat. If it was too high, you gained heat. Because the absolute value of negative 137, because remember, this is just coming from if it gets hotter or colder. Because 137 is less than 151, you lost heat. And would that account for the discrepancy? And so this is what the scoring guidelines say. Yes, because the magnitude, they're using the word magnitude. That means absolute value in chemistry. The magnitude is too low. And this is caused by delta T, remember Q equals MC delta T, being too low. And why is delta T too low? Because some of the heat leaked to the environment because we didn't have a really, really high-tech bomb calorimeter where you were using a coffee cup. And so, yes, with delta T being smaller because the heat leaked from the calorimeter into the air or the lab bench, whatever. So that's it. I'm going to stop this 22-minute lecture and see you tomorrow.